To complete this related rates word problem, we first need to read the problem carefully so we can get a sense of what we've been given and what we need to find. We also want to get a picture drawn if necessary and label the picture so that we have some variables to work with, and just make sure that we can translate the information from our word problem into some notation that we can use for math. So as we read this, we see a cylindrical can. So this keyword here, cylindrical, tells us the shape of the object we're looking at. So cylindrical means cylinder here. So we can go ahead and draw a cylinder just so that we can kind of get started here with the problem. So here's our cylinder. And so we have a cylindrical can with diameter 6 inches. So we're given this piece of information. The diameter of this can is 6 inches. So we're really looking at this distance right here. Diameter would be 6 inches. For the can. And it says in height 14 inches. So the height of this can here is 14 inches, so we'd be looking at this distance here being 14 inches. Okay. Of course, that can doesn't change in size. The can itself has those dimensions, but what could be inside the can could be changing in size. So that can is filled with tomato soup. How fast is the depth of the soup in the can changing? So we're looking at this being the question. How fast is the depth of the soup in the can changing? If the soup is being poured out of the can and into a pot at a rate of 10 cubic inches per second. So the one other thing we have here is this 10 cubic inches per second. Okay. So we want to figure out what is it that's 10 cubic inches per second. And right now we don't even have any variables at all to work with. So when we're looking at a cylinder, we typically have a radius and a height for the cylinder that describes the cylinder. So we don't actually, we're not actually interested in how the can would be changing because it's not changing. But we know that the amount of soup that's in the can is changing. So let's say that's the top of the soup at some point here. So the amount of soup is actually in the shape of a cylinder. That cylinder for the soup has a fixed radius. It never changes. That radius there would be half of the diameter of the can. So that would be a 3 inches, and that is the radius, and that is a constant. When you're pouring out soup and then you set the can back up, your radius isn't going to be changing. The amount of soup is always going to have the radius of 3 inches. But what is changing is the height of the soup. So that height there, it's going to be measured in inches because everything else in the problem is measured in inches. That would be a variable. That would be changing. So also, when we're talking about amount of soup, we're really talking about a volume of soup. So we're looking at the equation that we're interested in being the volume equation for a cylinder, and that would be pi volume equals V equals pi r squared h. And that would be the pi r squared, which would be the area of the circular base times the height of the cylinder. And so we know that the R is fixed, that radius is constant as we pour out the soup. So really we can go ahead and plug in the 3 for the radius. But we need to leave the H as an unknown, as a variable. So we're looking at the equation volume equals 9 pi times H. Okay. Now back to this 10 inches cubed per second. What is that? So it says into the pot at a rate of 10 cubic inches per second. So the tomato soup is being poured out of the pot at that particular rate. So we're really talking about the rate of change of volume there. And we get that clue based also on the units that we see. Inches cubed would be a measurement of volume. And so we're talking about a change in volume, the dV, over the S there for seconds would be the measurement of time, so it would be the rate of change of volume over time. The one other thing we need to pay attention to is the sign. This ends up being that the dV dt should be a negative amount because it's losing volume. Over time we're getting less volume, so the rate of change is going to be a negative value. So then back to what is it that we're trying to find. Back to our question up here. Here's our question. how fast is the depth of the soup in the can changing? So that depth is the H. And so we're looking at how fast is it changing. So we're really looking at a rate of change of H over time. That's what we don't know. We could figure out what the units are, because just like the dV/dt units are the units of volume over the units of time, the dH/dt units would be the units for the height, which would be inches, over the units for time, which would be seconds. We also know that conceptually the height is getting smaller over time, so conceptually we should know that this should be a negative value. So we have our setup complete, we have our variables in there, and now we're ready to take the derivative with respect to t on both sides. So we d dt, the volume, and then that would be the d dt of the right-hand side, which would be 9 pi h. Okay. When we take the derivative of the volume, we're talking about really some pretty good notation there. The d dt of v is notationally dv dt, because it's how much is the volume changing over time. On the right-hand side of the equation, we're looking at d dt of a constant, 9 pi, times the variable h. So using the constant multiple rule, the constant that's sitting out front just stays out front, and it would then be left with the d dt of h, so the derivative of h with respect to t. So that would be our relationship between the change in volume, for which we have a value, and the change in height, for which we're looking. So when we go ahead and substitute in, we know the dV dt is the negative 10, and then we have 9 pi dH dt. And we want to solve this for dH dt, and we can do so by dividing both sides by the 9 pi, that's the constant out front, to get our final answer. So negative 10 over 9 pi, and again the units there would be inches per second. So that would be our final answer. Notice how it is also negative, like we anticipated it would be.